This particular section deals with limits, and the limits that we're going to be performing are limits as x approaches infinity. So first of all, just imagine what that means. So as you're looking at a function, you're sending x to infinity all the way off the page that way, or you're sending x to negative infinity all the way off the page that way, and you're asking the question, what is happening to my function at the very ends? What's the end behavior of my function? Now, there are some possibilities here. One possibility is that the function settles down on a particular y value, which would be a horizontal asymptote, and sort of rides that right off the page to infinity. The other option is that the function takes off and goes off the page that way, in which case y is going to infinity as x is going to infinity, or the opposite, y could be going down to minus infinity. So we need to explore these options because I'm going to be using this to help us graph. And we need to put all the tools together for graphing, including everything we learned about critical numbers and relative maxes and mins. We also have to finish the problem off by saying, at the very end, what happens to this function? Does it settle down on a y value, horizontal asymptote, or does it shoot off the page either this way or that way? And that will help us graph it. So let's begin. And in order to do limits at infinity, we need to bring back our limits. And the limits at infinity look like this. And this is we'll call this the right end behavior. That's what that limit would tell us once we evaluate that. And then this limit, this would be the left end behavior. Now, these two limits, once I evaluate them, will really hopefully tell the story. If the limit ends up being a constant, like 10, it says as x is getting larger and larger, y is trying to approach 10. In fact, 10 is a horizontal asymptote. As x approaches minus infinity, if this limit becomes infinite itself, that means when x goes all the way to the left of the page, all the way off to the left, the y value is going off the page to infinity. So we need to be able to evaluate limits. Let's remember something. 0 over 0, or infinity over infinity. These are called the indeterminate forms. Now, while these are potentially answers for functions, you could plug an x value into a function and out comes 0 over 0. What do you say about that function? It's undefined. Probably because there's a tiny hole right where you want to make that evaluation. If you plug some x in and you get infinity over infinity, what does that mean for the function? It means it's undefined. Probably for the same reason. There's probably a little hole there. So while the function would be undefined, we never use these to answer limit questions. In fact, when you get these, what that usually indicates is a signal to dig a little deeper into that limit. So be careful. When you run your limits and you get these indeterminate forms, we never say D, N, E. We dig deeper to get the real answer. All right, so with that in mind, let's take a look at some end behavior. Let's start with this first function, which is 3x squared over x squared plus 1. Now, without really graphing it, let's just do this analytically by asking the question, what is the limit as x approaches infinity of my function? And let's talk about what that's really asking. It's saying send x right off the page to infinity, and what's going on out here with its y value? Is it settling in on a y value, or is it shooting off the page this way, or maybe the other way? Let's do it. Let's run this limit. Now, I did say when we came to limits, we always tried direct substitution first, and I want you to try it here as well. So I wonder if it's equal to this. Now, infinity squared is infinity, right? Can't get any bigger than infinity. And 3 times infinity is also infinity. Infinity squared plus 1, you just can't get any higher. And no, as we had pointed out before, that is never, ever a valid answer for a limit. We always cross that off. That indicates that we better dig deeper into this problem to really learn what our limit is. So let's do that. Now I've got some guidelines for you. And if you want to do this analytically, what you want to do here on these fractions is I'd like you to multiply the numerator and denominator by 1 divided by x to the n, where n is the highest power of x, but not in the entire problem, only in the denominator. Now, if we're going to multiply both the numerator and the denominator, you know we're allowed to do this. You can do this with any fraction. You can multiply by 2 on top, 2 on the bottom. It doesn't change anything in terms of its value. So I am going to play by the rules. I'm going to multiply the top and bottom by the same stuff, but it's good to know what this stuff is that will help get you to the answer we're looking for this problem. And again, it's 1 over the highest power of x in the denominator. So let's give it a shot. The limit as x approaches infinity of this particular function to learn its end behavior. Multiply by 1 over the highest power of x in the denominator, which happens to be x squared. So you do get a new limit, which is the limit as x approaches infinity. Well, this is going to be a little distributive law here, but these two go together naturally. So 3x squared divided by x squared. That's just 3. On the bottom, I have x squared divided by x squared. That's just 1. And here I have 1 over x squared. Let's see if this new version delivers the goods. Now you can plug in with direct substitution infinity and see what happens. So is it really equal to this? Direct substitution, 1 plus 1 over infinity squared. That's 3 over 1 plus, really 1 over infinity, right? But wait a second. Anytime you take a finite number and divide by 0, you get infinity. Anytime you take a finite number and divide by infinity, you get 0. So it's 3 over 1 is 3. So the end behavior for this function is it does stuff in the middle, whatever that is, and you can find out by looking for look for the intercepts, look for axis of symmetry, let's say, if it has any symmetrical aspects to it. Look for the relative maxes and mins, certainly interesting spots. So you'll know all about the middle behavior by doing that. But the end behavior is when this function is done going up and down and doing whatever it wants to do in the middle, it ultimately settles down and says, I'm headed to y value 3. And y value 3 acts like a magnet. The higher x becomes, the stronger the magnet becomes. And that would be a horizontal asymptote. That's what it is. When x gets really large and y actually doesn't change much, it settles down on a particular y value, we draw a horizontal asymptote. I have one other question before we continue, and that's this. This explored the right end behavior. So now we know that when x gets really big and positive, y tries to get to 3 as best it can. My question is, what about the other way around when we go to the left? We call this the left-hand behavior. Same function. And same problem. If you do direct substitution, which I encourage you to at least try, you get this. Negative squared's positive. Well, you see where we're headed with this. Infinity over infinity. We know that's never a good answer for a limit. We should never leave that as your limit. So we're going to try again. But this time, same exact procedure as before. I want to see 1 over the highest power of x only in the denominator. Now you do both, but when you're looking for the highest power, you go to the denominator to get that highest power. All right, what's our new limit? We're still going to the left here, guys, next to negative infinity, but 3x squared over x squared is still 3. X squared over x squared is still 1, and 1 over x squared is still 1 over x squared. I don't think really much changed here. Plug in your infinity, directly substitute, and you get this. Well, that's 3 over 1 plus 1 over infinity, right, which is 0, and that's 3 a second time. Okay. So far, everything has really stated clearly to us that there is a horizontal asymptote straight across in both directions. If you get really big in one direction, you go to 3. If you get really big in the other direction, you go to 3. So that's a nice, solid horizontal asymptote. And let me talk about horizontal asymptotes. Horizontal asymptotes, I want you to think of them as magnets. And what they do is when x gets larger and larger and larger, the magnet becomes more and more powerful. Horizontal asymptotes are permeable. What I mean by that is you can bust right through them. Okay, you can go through a horizontal asymptote anytime. But the magnet, if you go through it, the magnet tries to pull it back down towards it, right? So you can actually oscillate across a horizontal asymptote, and that's perfectly fine. You could do that. Vertical asymptotes, solid brick walls. There's no penetrating a vertical asymptote whatsoever. So just because you have a horizontal asymptote, don't believe that you can't go through it. You can. But just imagine the magnetic strength getting stronger and stronger as x gets larger. Okay, so what do we believe here? Well, according to what we just saw, my belief is that looks to me like we have a horizontal asymptote at y equals 3. And this horizontal asymptote seems to be working in both directions, both to the left and to the right. What I'd like to do now is I'd like to bring up my big graphing calculator on the computer here, and I'd like to just take a look at this graph to see if we can verify that we're getting what we expect to get here. So give me 1 second here to fire this up, and we should see a nice clean horizontal asymptote. So what I use typically in class here, I use this Desmos graphing calculator because it's really a nice simple calculator, graphing calculator, so you can actually just put the function right in there. So we're going to say that y is equal to 3x squared divided by, in parentheses, x squared plus 1. Can everybody see it? Sure enough, right here, the end behavior right here is 3 on both sides. Now, you could zoom in, you could zoom out, but no matter what, you could zoom out as far as the eye can see, and that thing is just lined up on 3 ever so nicely. And it will do that forever and ever. So again, imagine it's a magnet, and the more you drift away from the middle, the more that magnet attracts our curve to y value 3. And you can see it happening right here, and then finally it lands right there at 3. Horizontal asymptotes, it'll never, well, in this case, it won't actually touch the y value 3 because it's not really oscillating. It is allowed to go through. It could be 3. That is possible, but I don't think that would happen in this one. So it's just going to get up there and skim along that 3 and get closer and closer and closer the further you go. Okay, so I think we got a good idea as to how you find horizontal asymptotes. If you run your limit as x approaches infinity or minus infinity, then if you get a finite quantity, that's what it is. Now, you typically don't have to run both limits. As you saw from that example, normally, unless it has a square root in the function, normally if you get a horizontal asymptote, it's good on both sides. So you could just do one of those. Just do x approaches infinity. All right. So I do want to look a little further into this. And I'll give you the definition of a horizontal asymptote. The y and y equals L is a horizontal asymptote on both sides, left and right, as long as the limit as x approaches infinity f of x is equal to the limit as x approaches minus infinity of f of x. And I guess if it's really a horizontal asymptote, you only need to do one of them, equals L. Plain and simple. Okay. Let's try another one here. This one is, I'd like to know the end behavior. Of this function. Now, to explore end behavior, and typically if there's no radical involved, you can just do one of them. You can just do the right side, for example, and explore what would happen. So the limit as x approaches infinity of 3x plus 1, 2x squared minus x minus 1. And, of course, direct substitution would be the first approach. So 3 infinities plus 1. Well, that's just infinity, right? And then we get 2 infinity squared minus an infinity minus 1. Well, as soon as you touch infinity, it's pretty hard to get away from it. So we are at infinity, and we know that is never going to be an answer for a limit, 0 over 0 or infinity over infinity. Always a good signal to dig a little deeper into this problem. Dig deeper. Let's find out what's going on with this thing. So let's use the guidelines I showed you earlier, and that is that we do the limit as x approaches infinity. Same function. But multiply by 1 over the highest power of x. 1 over the highest power of x. Oh, in the denominator, that would be x squared. So we get a new function that we can run our limit on, and let's see what that is. Now, let's read this off here. 3x divided by x squared, that's actually 3 over x. 1 divided by x squared is 1 over x squared. That's what's on top up there. Down below, 2x squared divided by x squared is 2, minus x over x squared, that's 1 over x, and minus 1 over x squared. Now, you can send x off to infinity. All these particular terms will go to 0, right? So I get 3 over infinity, that goes to 0. I get 1 over infinity squared, which is 1 over infinity, also going to 0. So I get 0 plus 0 up top there. Now I hope I don't get 0 on the bottom, because if you do, we have to cross it off and start over. But look at that nice solid 2 down there. Minus 1 over infinity, which is 0, minus 1 over infinity squared is also 0. And 0 over 2 is a perfectly good answer. It's 0. So what do we do with this? What's 0 mean? Well, you ran a limit as x approaches infinity. Your limit was a scalar finite quantity here, L. So it's a horizontal asymptote. There must be a horizontal asymptote at y equals 0. Which is right here. It's the x-axis is a horizontal asymptote. Now remember, this curve will be magnetically attracted to y equals 0 the larger x gets. In the middle here, the magnet's barely on, and it won't be that attracted to it. So let's go ahead and, I think maybe graphing this would be a good idea. So same thing. Let me switch over to our graphing computer here, our little Desmos. And let's see what will happen now. So on the top of our fraction, we have 3x plus 1. On the bottom of our fraction, we have 2x squared minus x minus 1. Some interesting stuff happened in the middle. Okay, we're not really looking at this middle behavior just yet. What I'm really interested in, right here, end behavior. Sure enough, the x-axis acted just like a magnet, attracting my curve as x got larger and larger in the negative direction, and also, same in this direction. The x-axis, y equals 0, acted just like a magnet, and the larger x got, the more powerful it got, and it attracted our curve to y equals 0. I want to try one more example, but so far the technique is working really well. It's 1 over the largest power of x, in the denominator though. For this one, the function is going to be 2x squared plus 3x minus 1 over x plus 1. How's that? And I'm not interested in middle behavior yet. That's going to be our next section. What I'm interested in is the end behavior. And the end behavior can always be evaluated through this particular limit. Now remember, direct substitution is always the first thing you should try. And I always say, is it really equal to this? That's 2 infinities squared, 3 infinities minus 1. Well, but that just is infinity, so that's not looking good. Down below, I get infinity plus 1, well, which is infinity, and we know that is never a valid answer. So, of course, we're going to have to work this one out. So, redraw the problem and be careful, because the guidelines tell us to multiply by 1 over the highest power of x, not that one, in the denominator. That would be this one. So the new thing we're going to write down, the new version of this function, would look something like this. 2x squared over x. That's 2x, isn't it? 3x over x, x's cancel. And minus 1 over x. That's what's on top now. Down below, x over x, that's 1. And 1 over x is 1 over x. Well, now I should be able to plug infinity in, and I hope I get a result out of this. So, 2 infinity, right? Plus 3 minus 1 over infinity. Well, I like 1 over infinity. That's 0. And this is a 1 plus 1 over another infinity, which is another 0. So, what are we getting? Infinity itself. Now, is that such a bad answer? It isn't a bad answer, actually. In fact, we will stick with this. We don't have to dig deeper at all because it is not indeterminate. We know precisely where this curve is going. Right off the scale to infinity, right? 0 over 0, confusing, right? We don't know what that's worth. That's why we call it the indeterminate form. Infinity over infinity is really kind of the same issue. We don't really know what that's worth. It's just undefined. Infinity is undefined. I get that. But I know what kind of undefined it is. It's huge. It's way up there. So apparently there is no horizontal asymptote. What is happening here is as x is getting larger and larger, y is also getting larger and larger. So I don't suspect that this curve has a horizontal asymptote. But what I do suspect is that as x gets big, the end behavior looks something like that, right off the scale. Now it is worth digging a little deeper, because what's going on the left side of this problem? I don't know. Is it going to infinity or maybe negative infinity? Let's find out. We already know direct substitution will fail, so we're going to skip that step, and we are going to multiply by 1 over x. It's really the same as before. So it's the limit as x approaches negative infinity, 2x on top, plus 3 minus 1 over x. Down below, I get 1 plus 1 over x, and now we put negative infinity in here. So we get negative 2 infinities plus 3 minus 1 over negative infinity, which is really plus 1 over. It doesn't matter. It's 0. Down below, you have 1 plus 1 over negative infinity. Well, it doesn't matter. It's 0. Well, what do we got here? Negative 2 infinities is really the same as negative infinity. So we're going down on the other side. That's the left side behavior. So no asymptotes for this problem. So I think the best thing to do here is let's explore it on the graphing calculator here online, and let's see if that behavior looks correct. So let's plug that same function in here. So this function was 2x squared plus 3x minus 1, and I want to divide that whole thing by x plus 1. Let's see if we get the end behavior we expect. Well, I'm way over here, so I got to go back to the origin to see what's going on here. And zoom out. And it looks to me like the end behavior is exactly what we expected. As we get larger and larger in x, boy, y just takes right off. There is no asymptote over there to limit that y value. Now let's go over here to the left. As x gets smaller and smaller in the left, negative values of x, look at y going further and further and further down. So I would say it's verified that that is correct. When x went to infinity, y went to infinity. When x went to negative infinity, y went to negative infinity. So that's another example of what you can expect when we do limits at infinity. Now, the ones that get tricky are the ones that have radicals in them. And the ones that have radicals in them, you're going to discover that there actually are typically two horizontal asymptotes, and you want to find both of them. And the horizontal asymptotes light up and work on different parts of the graph. One of them works on the left side, one of them works on the right side. So let's see if we can figure that out. I'm going to give you a problem that has a radical in it, and we're going to try to work this through with the method that we have, which is 1 over the highest power of x, and see what happens. Before I do that, I need to show you something. You've probably always done this throughout your entire mathematical career. Square root and square cancel, give me x, right? In fact, we could test that theory. X equals 3. This would be the square root of 3 squared, which would be the square root of 9, which is equal to 3. And x is 3, right? So well, I've got some news for you, and that is that only works 50% of the time. So I'm going to show you a counterexample. I'm going to show you a situation where that does not work. So we've been doing this a lot, haven't we? Square root of x squared is x. Always. We write down x. It's not always true. And this is really important for doing these limits at infinity for these radical problems. So what's the counterexample? Counterexample means it's going to break this. Let's try x equals negative 2. Is it really true that the square root of that x squared, are you really equal to x like you're supposed to? So let's put it in here and over here. So the question becomes, is the square root of x squared really equal to that x? Now, negative 2 squared is 4, correct? Okay, is the square root of 4 really equal to negative 2? Is 2 really equal to negative 2? No. So, you know when we write the square root of x squared equals x, and we do that a lot sometimes when not really thinking about it, did you know that 50% of the time it's actually wrong? So we need to qualify this square root of x squared thing, and I need to give you a better definition so that we know what to do in this situation. For x's that are positive, you can state with confidence that the square root of x squared is truly x. No problems there. But for x's that are negative, you cannot do that. I just showed you that it doesn't work. What you're going to have to do instead is state that the square root of x squared is not x, it's minus x. So if you've never seen this before, it's quite the revelation, and it is something that we definitely are going to need to make this right. But let's test this. Does this really work? This should be true, hopefully. Let's test x equals negative 3, and let's see if it works. So the square root of x squared, are you really equal to negative x? The square root of 9, are you really equal, negative 3? Yes, you are. All right. So we've got to be really careful when we run into the square root of x squared, apparently. So here's what we're going to do. I'm going to do two limits. This one which will help us learn what the end behavior to the right is for that particular function. And then let's also do this one. And that one will tell me the left end behavior. Now with radicals, I do suspect that these are going to be different. You'll see how they become different, and then we'll graph this function so that we can prove that we really end up with two horizontal asymptotes. Let's start with the first one. The limit as x approaches infinity of 3x minus 2 over the square root of 2x squared plus 1. I will tell you, I'm not even going to write it this time, if you directly substitute it in, you get infinity up here, infinity squared, square root, doesn't matter, you're at infinity over infinity, never the answer for a limit. So, we talked about the method, right? The method is to multiply by 1 over the highest power of x in the denominator. Not 2x squared, just the power of x itself. And whatever we do down here, we got to do up there. Now, take a look at what you're about to do. You've got a radical multiplied by a non-radical, and they're not going to go together very nicely, really. What I'd really prefer is that this somehow gets inside here, and the only way it's going to do that is if I give it a little help. Okay, so it's 1 over the highest power of x, but this needs a radical so that these two will join together. Now, on top, I got to multiply by that same exact thing. Here we go. Now the problem on top is you got a radical multiplied by a non-radical, and it's the same situation as before. They're not going to go together too nicely, really. But we can simplify this radical. And look what I just ran into, the square root of x squared right there in the corner. So on the top, you can actually multiply by 1 over. Now, should I write an x here? And the answer is yes. Because look where we are. X is approaching infinity, meaning x is positive. You can't be more positive than that. And when x is positive, the square root of x squared is the letter x. So we're going to multiply the top by this and the bottom by that. All right, let's work this one out. So it's going to be 3x minus 2 multiplied by 1 over x on top. It's going to be the square root of 2x squared plus 1 multiplied by a square root, thankfully, so they do go together on the bottom. What do we get from all that? Let's find out. 3x over x is 3, and 2 over x. That's what I get on top. Now, you know the two radicals will go together into one big radical, so we can actually multiply just these two together inside the radical. 2x squared over x squared is 2, and then 1 over x squared is what's inside. Let's see what we got. So continuing and completing this limit, I get the limit as x approaches infinity, 3 minus 2 over x, square root of 2 plus 1 over x squared, and now go right ahead and plug it in with direct substitution. That would be 3 minus 2 over infinity, which is worth 0, and square root of 2 plus 1 over infinity squared, which is also worth 0. So in the end, I found my limit. And if you don't like the radical on the bottom, I certainly can take care of that with rationalizing the denominator to get this in simplest radical form. So, apparently, on this particular function, when x gets large enough towards infinity, y is settling down at 3 square roots of 2 over 2. Let's see what that's worth numerically. It's approximately 2.12. So we should see on our curve that when x gets really big in the positive direction, y should settle in on this horizontal asymptote. Okay? So that's what we should see on the graph once we do graph this. All right, I did say with radicals, we tend to have two asymptotes, one on each side. So unfortunately, we have to repeat the problem. But this time I want x to approach minus infinity on the same function. And you're going to see the very, very subtle twist to this problem in just a moment. So now, I'd like to multiply by 1 over the highest power of x in the denominator. You got to do the same top and bottom. We're always obligated, right? Now, this radical will not join with that, so we require a radical. Got to do the same top and the bottom. These go together quite nicely. These do not. So how do we make the top go together? Well, let's simplify. Up top, you have a square root of 1 and a square root of x squared. Square root of 1 is 1. And what is square root of x squared worth again? Is it x? Well, wait a second. You're in negative x territory. In fact, you couldn't be much more negative than that. All right? So square root of x squared, when you're in negative territory, is not x. It's minus x. So that's what we need to put here. And that's that very, very subtle twist to this problem. It's because of where you are. You know where you are in negative x territory. That's when square root of x squared starts spitting out a minus x, actually, strangely enough. So the limit becomes this. Let's multiply 3x minus 2 on top by negative 1 over x. You can move the negative to the top. That's fine. And then we're going to do square root of 2x squared plus 1 multiplied by square root. You know the square roots go together. And what's that limit going to look like? Let's find out. So I get 3x divided by x with a minus sign. What's that worth? Isn't the x's cancel? I'm left with a minus 3. A negative 2 times a negative 1 over x is a plus 2 over x. These two radicals love to join together. So 2x squared over x squared is 2, and 1 over x squared is 1 over x squared. Now, only now do we really, truly get to plug our limit into the problem. So I'm going to recopy it here, and then let's put it right in as a direct substitution. So we directly substitute right in there. And what do we get? Minus 3 on top, 2 over minus infinity. Doesn't matter, it's 0. And down below, you get a 2 plus 1 over minus infinity squared worth 0. And so our limit ends up being this. Minus 3 over square root of 2. If you don't like the radical on the bottom, I can certainly fix that. And that is minus 2.12 approximately. And that will be another horizontal asymptote. So I think what we need to do is really talk about what just happened, what kind of behavior we're getting. There are two asymptotes, one on the left and one on the right. So the asymptote on the right side, when x gets really large, is approximately 2.12, and therefore it lights up like a magnet up there at y equals 2.12, and the curve will be attracted to it. Over on the left side, we got y equals minus 2.12. That's a little lower, and then that should light up like a magnet. Why don't we take a look at this particular curve? I'm going to center up my graphing computer here, and then punch that curve in, and we ought to see just that. So what's our function again? Y equals 3x minus 2 in parentheses. We're going to divide that by the square root of 2x squared plus 1. Well, take a close look, guys. As promised, on the right side, 2.12 is just a little bit above this line here, lit up very nicely. And the further we go, and you can actually just barely see that it lives slightly above the 2, which is precisely what we would have expected. Just kind of a tiny bit above the 2, because it's 2.12. Now, over on this other side, we'll zoom out a little bit here. Same thing happened on the left side. We're down to minus 2.12. Same thing. It's just a tiny bit below the minus 2 line. This is the minus 2 line right here. So everything that we expected happened, and the middle behavior is another matter entirely. We'll talk about that in the next video. So I've given you the guidelines for doing limits as x approaches infinity or minus infinity. For most problems, there's going to be one asymptote if there is going to be a horizontal asymptote, and you don't have to do both. You can just do one. X approaches infinity. For a problem with a radical, there are two horizontal asymptotes, and to really get both of them, you have to run the limit to infinity and minus infinity and evaluate. And what was the big revelation that we had? That was that the square root of x squared equals x only 50% of the time. When x is known to be negative, the square root of x squared is minus x. And we needed that up there in the numerator to get those things to multiply together. So this will equip you with everything you need to do curve sketching, which is the next video. In that video, we're going to put it all together. Everything we learned in like pre-calculus, let's say, everything we learned for critical numbers and relative maxes and mins, and then also this end behavior on top of that. And we'll be able to really accurately graph some curves. And that'll be the next video. Thanks, everyone.